Hello and welcome to this presentation related to friction in square screw threads. This presentation does require some background information and theory from previous presentations. So before reviewing this presentation, it's preferable that you review the presentation related to the simple friction model, presentation related to construction of force vector diagrams, of friction on an inclined plane, and also the simple machines presentation specifically related to screw threads and screw jacks. The knowledge and theory from these particular topic areas underpin the work we're going to review in this presentation. Here's a presentation overview. We commence with an introduction, recapping some basic knowledge from previous presentations. We outline the nomenclature used, we review multi-screw threads, and we state some basic formulae that will underpin the presentation. We then consider motion up the inclined plane due to a horizontal force P applied to our screw thread. We then consider motion down the inclined plane due to a horizontal force P applied. From these two analyses of motion up and down the inclined plane, we derive relevant formulae which we can then apply to solving problems associated with friction in screw threads. We briefly outline the effect of overhauling of screw threads. Then we have example 1, where we use the equations that have been derived to calculate the torque required to raise and lower a load and the efficiency of the screw thread. Then we have 3 exercises for you to undertake. Again, finding the torque required to rotate a double start screw thread. Exercise 2, find the torque required to rotate a turnbuckle and the efficiency of the screw thread. Exercise 3, we have to find the torque required to raise a screw jack and also the friction coefficient for the given situation. Note the full work solutions are shown to all the exercises. Finally, there are some questions for you to attempt at your own pace and to develop your own solutions. And here are the approximate start times related to the various sections contained within the presentation. Please note all times are rounded to the nearest minute, and also that the nomenclature section starts at both 6 minutes into the presentation and also continues at 8 minutes into the presentation. Here's some terminology, mostly a recap from our simple machines presentation. I'll let you review these definitions at your own pace. We are essentially going to be considering square thread forms within the analysis and the calculations undertaken here. But as outlined in the previous presentation, square threads are normally very difficult to manufacture, so the Acme thread form is often used. That has the plain shape of a trapezium. We define pitch, P again here, sometimes referred to as pitch lengths, lowercase p for pitch shown in these diagrams here. Also define the lead, symbol capital L, shown here in our diagram. This is a diagram of a 3-start thread. So lowercase n is equal to 3 here, and the lead is equal to the number of starts multiplied by the pitch. Also stated a definition of overhauling. This is something we'll be reviewing later in the presentation. An overhauling essentially relates to a situation where an axial load W causes downward movement without the application of a torque to the screw thread. So we need to be careful that overhauling does not occur in practice, or we have mechanisms in place to prevent overhauling from occurring. So let's commence the analysis of friction in square screw threads. Figure 1 here shows the screw thread geometry. On the right hand side here we have our thread with the applied axial load W acting downwards here, pitch lowercase p denoted here, and some terminology. We have the core diameter, the thread shank, we have the mean diameter and the outside diameter. And from our previous presentation, we know that a screw thread can be analysed as essentially a load being moved up an inclined plane, and that's shown here. This inclined plane is essentially the unwrapping of the helix of the thread. Here's a recap from our previous presentation related to development of the helix, which generates the inclined plane. The sketch in figure 2 here shows the screw thread development for a single start square thread, and this development of the thread is essentially the inclined plane shown here. and the thread's formed by the unwrapping of the plane around the core of the screw, which of course is in the form of a helix. That's just a recap slide from our previous presentation. So in one revolution, the force applied to the thread has moved through the circumference of the thread, that's pi d here, and that's caused the load W to move through a height in this case, which is essentially the lead of the thread, and the lead is the number of starts multiplied by the pitch of the thread. Now angle alpha is the angle of the helix, and of course the angle of the inclined plane. And this right angle triangle here is a force vector diagram where we have horizontally applied force P to our screw thread. We have the weight force acting down, W shown here on our diagram. So force R, shown here on our force vector diagram, shown here on our free body diagram, is the reaction to the applied forces P and W. As already mentioned, angle alpha is the helix angle, and this angle here denoted as phi is termed the friction angle. So this angle in our triangle is the alpha plus the phi. Further recap, let's consider multiple screw threads. Again, this is an extract from our previous presentation. Multiple screw threads are used when the pitch of a screw is required to be larger than is usual for the given diameter. In other words, one revolution of the screw moves a larger distance than would be expected for a standard screw of a particular diameter. So although multiple screw threads provide this larger movement, there is implicitly a loss of strength because there are less threads per unit length. So this loss of strength is accommodated by making the screw multi-threaded. This means that several threads are now cut, each parallel to each other, and of course having the same pitch. So for a single threaded screw, when lowercase n is equal to 1, the lead is equal to the pitch. For a double threaded screw, when n is equal to 2, the lead will be twice the pitch, and for a treble threaded screw, a 3-start thread, n is equal to 3, and the lead will be 3 times the pitch. So that's an overview of multiple start screw threads. Here's a listing of the full nomenclature used within this presentation, some of which we've already mentioned. Angle alpha is the angle of the helix, that'll be in degrees. Angle phi is the friction angle, again in degrees. Symbol eta is used for efficiency of the screw thread, it's dimensionless. And symbol mu is the coefficient of friction, and again that will be dimensionless. Capital D will be the mean or the effective diameter of the screw thread in meters or sometimes millimeters. F suffix F is the friction force in newtons. Capital N is our normal reaction force in newtons. Lowercase n is the number of starts on the screw thread. That will be assumed to be 1 unless otherwise stated. Lowercase p is the pitch of the thread in meters or millimeters. Capital L is the lead. That's the linear movement of the thread in one revolution, which is the number of starts multiplied by the pitch, and again that will be in meters or millimeters. Capital P is the applied horizontal force to the screw thread in newtons, and capital R is the reaction force from the inclined plane, that's in newtons. Capital T is the applied torque in newton meters, and capital W is the actual load that's being raised or lowered, that's in newtons. Here are some relevant formulae. The coefficient of friction, symbol mu, is equal to tan of angle phi. From this right angle triangle here is the normal force at right angles to the inclined plane. Here is our frictional force acting parallel to the inclined plane, and here is angle phi. So from basic trigonometry, we know that tan phi is the opposite side of the triangle, FF, divided by the adjacent side of the triangle, the normal force N. Recalling from our simple friction model, which relates to a separate presentation, the frictional force is calculated from the formula coefficient of friction mu multiplied by normal force N. So rearranging this equation for mu produces this equation. So tan of phi is equal to mu. Relevant formulae continued. Tan of angle alpha being the helix angle of the inclined plane, is equal to the lead of the thread per one revolution, number of starts times the pitch, shown here from B to C, divided by pi d. Pi d is the circumference of one revolution of the thread, or equivalent to the inclined plane, shown here. Relevant formulae continued. Let's consider efficiency, symbol eta. Efficiency is the work done on the load, W, in one revolution. Remember from a previous presentation, work done is force multiplied by the distance travelled, or the displacement. So that's W multiplied by the lead, or W multiplied by NP. And that's divided by the work done by the input force, P, in one revolution. So the horizontal applied force P to the thread diameter produces work done of P multiplied by pi d. But from figure 1 on our previous slide, extract shown here for reference, we know that P divided by W is equal to tan of alpha plus phi, angle alpha plus phi shown here, and the lead shown here divided by pi d here is equal to tan alpha, helix angle alpha shown here. So replacing W upon P here with P upon W here, we will have in the denominator tan of alpha plus phi, and replacing the lead NP divided by pi d with tan alpha, efficiency can be shown to be tan alpha divided by tan alpha plus phi. Now note that torque, capital T, is force P multiplied by radius, shown here is diameter divided by 2, then rearranging force P is twice the torque divided by diameter d. So considering this equation and replacing P with this equation, d will cancel top and bottom, and we will have 2 multiplied by t on the bottom line. So essentially this exercise has shown we can derive 2 equations for efficiency. One is tan alpha divided by tan alpha plus phi, and the other is W multiplied by NP divided by T multiplied by 2 pi. And for clarity, here's a more detailed breakdown of the transposition required to prove the formula for efficiency as shown on the previous slide. I'll let you review this slide at your own pace. Just note for reference that if the efficiency is greater than 50%, the thread will overhole. In other words, not self-lock. Let's consider motion up the inclined plane due to a horizontal force. Here's our free body diagram of the block being pushed up the incline. The force P horizontally applied, our weight force act vertically down, our frictional force opposing the upward motion, and our normal force at right angles to the incline. So what we've done next is resolve forces parallel and perpendicular to the incline. Note angle alpha is the angle of the helix or angle of the incline here. So considering the weight resolved parallel and perpendicular to the incline, the parallel component is W sine alpha, that has a direction down the incline, and the perpendicular force to the incline is W cos alpha, shown in this direction. Resolving force P parallel to the incline, we have P cos of alpha, shown here, and normal to the incline, P sine of alpha, shown here. We can now use this free body diagram to resolve our forces parallel to and perpendicular to the incline. Motion up the inclined plane continued. Just repeated the free body diagram here for reference. So resolving forces parallel to the incline, we have P cos of alpha, this component here, up the incline, is equal to the friction force, shown here, shown down the incline, plus W sine of alpha, shown here, the component going down the incline. We then note that the friction force is actually equal to mu n, so replacing friction force with mu n. Now resolving forces perpendicular to the incline, we can see that the normal force, labelled n here, in this direction, must be equal to W cos of alpha, this component here, in this direction, plus P sine of alpha, this component here, in this direction. So inserting these components for n, here and here, we can next expand the brackets, shown here, then collect all the terms, the P variable, onto one side of the equation. So on the next line we subtracted mu P sine alpha from both sides of the equation. We then factorize on P. We then divide throughout by cos of alpha on the next line. So each of these terms are now divided by cos of alpha. So cos alpha divided by cos alpha will be 1. Mu sine alpha divided by cos alpha will be mu tan alpha. On the right hand side, mu w cos alpha divided by cos alpha will be mu w. And w sine alpha divided by cos alpha will be w tan alpha. Motion up the inclined plane continued. Just repeated this line for convenience from the previous slide. On the next line we divided throughout by 1 minus mu tan alpha, and we factorised the numerator on weight force W. On the next line we replaced the mu with tan phi. We proved the relationship mu is equal to tan phi on a previous slide, shown here on this slide. And we've also replaced the mu in the denominator with tan phi, shown here. So using compound angle theory, a topic we reviewed in a previous presentation, we can show that force P is actually equal to W tan of alpha plus phi. Here's our compound angular formulae from our previous presentation, and its equation labelled here is 3 that we're going to use to simplify our formula for P. So we know P is equal to the W tan phi plus tan alpha over 1 minus tan phi tan alpha. So referring to equation 3a here, which is an expanded version of equation 3, we can see that angle phi in our derived formula is analogous to angle A in our compound angle formula here and here, represents the two phi terms, and angle alpha is angle B in the compound angle formula, shown here and here. So that's how we can use then the compound angle formula to simplify the right hand side into simply tan of A plus B. So tan of alpha plus phi. And if we want to calculate the torque T required to raise the load, we know that T is equal to force P multiplied by the radius, or d upon 2. So we can write torque T is equal to W tan alpha plus phi multiplied by d upon 2. The only change in the final bolded box here is that the torque is shown to equal a half of WD tan alpha plus phi, just a slight rearrangement of the previous line. So now we have a formula to calculate the force required to raise a load using a screw thread, and also the torque required to raise the load using a screw thread. If we now consider motion down the inclined plane when a horizontal force P is applied, we can draw another free body diagram, but this time force P applied horizontally is pulling the block down the inclined plane. Of course, the weight force still acts vertically down, but the friction force opposing the relative motion now will be shown to act up the inclined plane. The solution involved with determining a formula for P is very similar to that we use for analysing motion up the inclined plane. So on the following slide I will show you the solution, but I'll let you review it at your own pace. So considering motion down the inclined plane when a horizontal force is applied, as before we resolve forces parallel to the incline. On the right hand side we have friction force shown here. That's showing up the inclined plane because the motion is down the inclined plane, and that's equal to P cos alpha shown here, it's down the inclined plane, plus W sine alpha shown here, and that's down the inclined plane. Friction force formula as before is mu n, but this time n is equal to W cos alpha And here on our free-body diagram, notice that's down towards the inclined plane minus p sine alpha. So a change of sign here because p sine alpha is shown in this direction, opposite to w cos alpha. From here on, the solution is very similar to that shown previously. I've labelled the solution here, so hopefully it makes it easier for you to follow. And applying compound angle theory again, we ultimately end up with a formula for force P, or horizontal force shown here, which is equal to W multiplied by tan of alpha minus phi. Notice the sign change here in the bracket. And if we want to determine the torque required to lower the load, in this case, torque T, is equal to a half multiplied by WD multiplied by tan alpha minus phi. We can compare these to the motion up the inclined plane, which showed the formula having alpha plus phi in the bracket. I would encourage you to stop the presentation and review the solution at your own pace. Motion down the inclined plane with a horizontal force applied. Continued. Let's consider the situation where alpha, the helix angle, is less than phi, the friction angle. So that's the scenario shown here in the top right hand diagram. So to calculate the force P required and the torque T required when alpha is less than phi, we can use the equation shown here. And notice that when phi is greater than alpha, the reaction force to forces P and W is shown in this sense. So in other words, the reaction force is preventing motion down the inclined plane. However, for a scenario where alpha is greater than phi, and so the force P and the torque T are calculated from these equations, the reaction force would now be in this direction and essentially forcing the load down the inclined plane under gravitational effects. The latter case is termed overhauling. Let's for a moment consider overhauling of a screw thread. So when a load moves down and overcomes the thread friction by its own weight, it is said to overhaul. In general, if the angle of the helix, alpha, is greater than the friction angle, phi, the load will accelerate downwards. So if alpha is greater than phi, overhauling occurs. Let's consider example 1. A screw jack carries a load of 4 kilonewtons. It has a square thread, single start screw of 20 millimeters pitch, 50 millimeters mean diameter. We're asked to determine the torque required to raise the load and the efficiency of the screw. We're also asked to determine the torque required to lower the load. The friction coefficient is given as 0.22. If it helps you form your solution, here's a list of all the equations we've proved within this presentation so far. Just thinking through the information given, we have the applied load W. We know it's a single start screw thread of 20 millimeters pitch, so we have N in P. We have the mean diameter given, it's capital D, and we have the friction coefficient given, symbol mu. So straight away we can calculate friction angle phi, helix angle alpha, so we can calculate the efficiency. And again, having calculated the alpha and the phi values, we can find the torque required to raise the given load W, and of course we can then calculate the torque required to lower the load given that alpha is less than phi, which we will determine from our calculations. I'd encourage you to stop the presentation, attempt example 1, but a full worked solution is shown on the following slides. So example 1, here's the commencement of the solution. As always, extract the information from the question, state appropriate symbols and units. Let you review this slide at your own pace. Example 1, solution continued. Just repeated this information for convenience from the previous slide. Firstly, using the value of mu, the friction coefficient, we've calculated the friction angle phi, that's tan to the negative 1 of mu. That evaluates to 12.41 degrees. And knowing the number of starts, 1 in this case, and the pitch, 20 millimeters, and also the diameter D, we can evaluate the tangent of alpha. So tan of alpha is 0.1273. So from the inverse tangent of alpha, the helix angle is 7.256 degrees. So note in this case that alpha is less than phi. So from our previous work, no overhauling will occur. In other words, the load will not lower freely under its own weight. Example 1, solution continued. So next we calculate the torque required to raise the load W, torque equation from our previous work given here. Inserting the values for W, D, phi and alpha. The torque required to raise the load is 35.7 Newton meters. Note here I use my diameter in terms of meters. Note for reference I use the pitch and the mean diameter in terms of millimeters, as the unit effectively cancels, as we have millimeters in the numerator and millimeters in the denominator. Just notice in this calculation the mean diameter was stated in the unit of the meter because I wanted the torque calculated in terms of the Newton meter. Next we calculate the efficiency of the system. We have our formula for efficiency. It's tan alpha divided by tan phi plus alpha, and again inserting the values. The efficiency calculates to be 0.356, or of course that's 35.6%. And finally we've calculated the torque required to lower the load. Again, here's our formula derived earlier. In this case alpha is less than phi, and again inserting the values. The torque required to lower the load is 9 Newton meters. That's the full solution to example 1. Here's exercise 1. A double start square thread screw drives a cutter of a machine tool against an axial load of 450 newtons. The external diameter of the screw is 52.5 millimeters and the pitch is 5 millimeters. If the coefficient of friction mu for the thread is 0.15, we've got to determine the torque required to rotate the screw. Answer is given in the bracket here. Again, if it helps, here's our listing of equations. From the question, we've got to determine the torque required to rotate the screw. You can interpret that as calculate the torque required to raise the load. As a hint, note in the question we're given the external diameter of the screw thread, but in our calculations we need to use the mean diameter. So we'll need to determine the mean diameter from the information given, knowing the external diameter and the pitch of the thread. Reference is the formula for calculating the mean diameter D. I'd encourage you to stop the presentation and attempt exercise 1, but the full work solution is shown on the following slides. Exercise 1, here's the commencement of the solution. Note in this case we have a double start square thread, so the n will equal to 2. Rest of the information extracted from the question. Converted my dimensions from millimeters to meters. Just note in this question we're actually given the external diameter. We will need to calculate the mean diameter in a moment. Exercise 1, solution continued. Now here's the calculation for the mean diameter D. It's the outside diameter minus half of the pitch. Here's the mean diameter calculation, a little more detail. So the mean diameter D is the outside diameter minus half the pitch. So note this is P upon 4 shown here and P upon 4 shown here. So outside diameter minus half the pitch. Evaluates to 50 millimeters in this case. So inserting the values, the mean diameter is 50 millimeters. We have the friction coefficient, so we can calculate the friction angle phi, and we can determine the tan alpha is np upon pi d. Again, inserting the values. Tan alpha is 0.2 divided by pi, or 0.2 pi to the negative 1, or in decimals that's approximately 0.063662. So we can now calculate helix angle alpha from the inverse tangent function at 3.643 degrees. Again, we notice that alpha is less than phi, so no overhauling occurs. We can now calculate the torque required to raise the load. We have the formula. We insert the values for load W, mean diameter, phi, and alpha. So the torque required is approximately 2.43 Newton meters to 2 decimal places. That's the full solution for exercise 1. Exercise 2, a turnbuckle, shown in the sketch here, has right and left hand screw threads of 10 millimeters pitch. This is the left hand thread, this is the right hand thread. The mean diameter of the thread is 40 millimeters and the coefficient of friction is 0.16. The turnbuckle is used to tighten a wire rope. If the tension in the rope is a constant 12 kilonewtons, we've got to calculate the turning moment or the torque required. We also have to calculate the efficiency of the system and then the torque required to slacken the turnbuckle. Answers shown in the bracket here. Again, if it helps, here's the full listing of equations. We have to calculate the torque required to tension the rope, the efficiency of the system, whichever formula you're required to use, and the torque required to slacken the turnbuckle. I'd encourage you to stop the presentation and attempt exercise 2, but the full work solution is shown on the following slides. Exercise 2 is the beginning of the solution. As always, let's extract the information from the question, calculate our friction angle, calculate angle alpha. Again, no overhauling occurs in this situation. Exercise 2, solution continued. So firstly, we calculate the torque required to tighten one thread. Don't forget there are 2 threads here effectively. The left hand and the right hand threads in our turnbuckle have to be turned. So I've calculated the torque required to turn one of the threads here, but the total torque required will be 116.48 Newton meters because we have these 2 threads here. Next, I've calculated the efficiency. I've actually used both formulae here. Efficiency in terms of the helix angle, the friction angle, calculated here in decimal and percentage. And of course we get exactly the same answer for efficiency if we use the WNP upon T multiplied by 2 pi equation and insert in the values for this equation. And finally we have to calculate the torque required to loosen both of the threads. Maybe that's TL here. So in this formula I've actually accounted for the 2 threads here, which simplifies the formula to WD multiplied by tan phi minus alpha. Insert in the values. The torque required to unscrew both threads is 38.1 Newton meters. That's the end of the solution for exercise 2. Exercise 3. A mass of 2 ton is raised by a single start square thread screw jack. The mass bears on a collar that does not revolve with the screw. Bearing collar shown here. The screw pitch is 12 millimeters and the outside diameter of the thread is 56 millimeters. The efficiency of the screw jack, and this accounts for both the screw thread and the collar friction effects at the given load, is 15%. We're given the torque required to overcome friction at the bearing collar is estimated to be 120 Newton meters. We've got to calculate the torque to overcome thread friction and also calculate the coefficient of friction for the screw thread. If it helps you think through your solution to exercise 3, here's the summary of formulae. As a hint, as you're given in the question the efficiency of the screw thread, theta, you'll be able to determine the torque required, T, to overcome the total friction in the system. You're given in the question that it's estimated 120 Newton meters torque is required to overcome the friction at the collar contact with the load. So knowing the overall torque, you can subtract from that the friction, and that will then provide you with the value of the torque required to overcome thread friction. From there you can use this equation, and knowing friction angle phi, you can then calculate the friction coefficient mu. So I'm not sure if those hints help you with your solution development, but I would encourage you to stop the presentation and attempt exercise 3, although the full work solution is shown on the following slides. So here's exercise 3, beginning of the solution. As always, extract the information from the question. Notice the load is in terms of 2 ton in the question, so I've converted that to newtons here. We're given in the question the external diameter, so again I've calculated the mean diameter. We're given in the question the torque required to overcome the bearing or collar friction. We're also given the efficiency of the jack, e to 15%, that's 0.15 of course. Again, that's less than 50%, so no overhaul will occur. From our usual formula, I've calculated the helix angle alpha. Exercise 3, solution continued. Because we're given the efficiency, so by rearranging the efficiency equation, we can calculate the total torque required for this particular load being raised. Inserting the values, the total torque is 250 Newton meters. So if we now subtract from the total torque, the torque estimated to overcome collar friction, 120 Newton meters, we can calculate the torque required to overcome the thread friction, 130 Newton meters here. Now we know the torque required to overcome the screw thread friction. We'll be able to calculate the friction angle and thus the friction coefficient. So transposing this equation, firstly for the tangent function, then take an inverse tan of both sides of the equation, because of course we know angle alpha, calculated on the previous slide, shown here. And hence we can calculate the friction coefficient in this particular instance, which is 0.185. So a slightly more complicated problem to solve in exercise 3, but the full solution has been shown here. Finally, I'll leave you with some tutorial questions to attempt at your own pace. So question 1 through to question 4 here. The answers are shown in the bracket on the right hand side. And here's the bibliography used to help generate the presentation, which I hope has been of interest to you, and as always, thank you for viewing.